Hi friends, we're going to start with the chapter called ammonia. This is the only base which we are going to study in the entire syllabus. We have hydrochloric acid, nitric acid, sulfuric acid. All acids and just a single base, just fighting for its position. But we are going to talk about it in depth. Okay, so talking about the chapter called ammonia. Ammonia, the molecular formula is NH3. Most of the kids, they get confused with the formula NH4 plus. That is an ammonium ion. It's a radical. This is a compound. Ammonia was said to be, it was called as alkaline air. Alkaline, now what's that? Can I say alkaline air means it's basic in nature. If you happen to taste ammonia, it's going to be bitter because it's a base, right? All right. Talking about the preparation of ammonia, we start with our first method of preparation, and that's the laboratory method of preparation. So guys, this is my first answer with your lab method of preparation of ammonia. All right. First, the flask, the round bottom flask in the experiment is tilted for a reason. Hold on now. I'll come over it. Okay, the round bottom flask is tilted and there is a burner at the bottom with a gentle heating. Okay, the reactants which we're going to use out here, right, it's going to be slaked lime, which is obviously taken in a higher ratio. A good amount, a good proportion of slaked lime is taken. We call it as calcium hydroxide. That is CaOH twice. It is a base. All right, and we have sal ammoniac. Now, sal ammoniac, guys. It is also called NH4Cl. I think you have heard about this. Yep, of course you have heard about this. This is ammonium chloride. The other name is sal ammoniac. And we have taken pieces of it, yeah, in this. By gentle heating, obviously, the reaction takes place and the gas which is evolved, it is ammonia gas, NH3. It is in gaseous form. Along with ammonia, guys, we also have moisture which comes up, right, with this? All right. Now, can I say that there are two gases coming or evolving after the experiment occurs? One is moisture and the second is ammonia. What we do is, I am interested in my ammonia gas. It's my ammonia. I have prepared it, right? Moisture, I want to throw it out. What I'm going to do is, moisture. Can I use a drying agent to remove the moisture? Of course you can. So now, what we're going to do is, we will pass this pipe through an inverted or a gas jar, okay, a gas jar, a cylindrical gas jar, where it contains a drying agent. So obviously there is some entry, and this is, you can say, this is a drying agent, and the one which you're going to use as a drying agent is calcium oxide. Okay, calcium oxide is used as a drying agent. I would say it is preferred as a drying agent. There are many drying agents in our syllabus, but why are they not opted for? I'll come to it. Just hold on. Let's go on with the process. So now, guys, the ammonia gas, come on, plus moisture, they are liberated. They come down. And now, once they reach this gas jar, the cylindrical vessel, can I say the calcium oxide absorbs all the moisture? Who is left out? It is ammonia, the dry ammonia gas. And that dry ammonia gas, there is another pipe, and we have an inverted. Now that's important. That's important for you all. We have an inverted jar which is clamped, okay, with the help of a stand. And this ammonia gas goes up, and out here we get dry NH3. Okay, it's collected this way. So this is how the apparatus looks. Now there are many questions which a student asks me. Sir, question number 1. Please tell us the reaction which takes place. Fine. Relatively fine. Can I say we have reacted these two reactants, right, with this? So we have NH4Cl, that's sal ammoniac, reacts with calcium hydroxide, COH twice. Alright. What happens is we get calcium chloride, CaCl2, plus NH3 plus moisture. Now if you happen to balance this, 2 chlorine, 1 chlorine. So you get a 2 out here. 1 nitrogen, 2 nitrogen. So you need a 2 to balance, right, guys? Okay. With this, chlorine is balanced and nitrogen is balanced. Calcium already balanced. Now what about hydrogen? 8 and 2, 10 hydrogen on the LHS. 6 and 2. Till now, 8 hydrogen. I want more. Let's put a 2 out here. That's it. And finally, 2 oxygen, 2 oxygen. That's balanced for you. Okay, students are very much convinced by the reaction. I say, don't be convinced. I have much more explanation for this one. Can I say, which gas are we making, all of you all? Oi, help me out. Which gas are we making? We're making ammonia. Now the rule is, to make ammonia gas, the salt used should be an ammonium salt. That's important. Isn't this ammonium chloride? Yes. So compulsion, the salt to be used in the preparation of ammonia has to compulsorily, mandatorily be ammonium salt. So you can have any of the ammonium salt, yeah? You can have ammonium chloride, ammonium phosphate, ammonium sulfate, right? Ammonium nitrate, so many salts, but the condition is ammonium salt. Remember that. So that's the reaction for you all. Second question, why the hell is this glass apparatus tilted? The reason, look, we know that even moisture comes up. When the moisture comes up, and if this apparatus would have been straightened, the moisture would have been collected, and after the condensation, the moisture, the water droplets would trickle back. Now, when the water droplets trickle back, this becomes somewhat an explosive reaction. Explosive reaction? Yes. It is a bit exothermic in nature. So it is risky, guys. So always remember one thing. We do not want the moisture to trickle back down, the water to trickle back down. My aim is that the entire ammonia and the entire moisture should pass down to the drying agent, and moisture should completely be absorbed. Second reason for me tilting this is the surface area increases, and if the surface area increases, the reaction takes place quicker. So I can say just the key words, the key pointers. First, tilt is because I don't want no moisture should trickle back. And second, surface area increases. And guys, if surface area increases, yes, the reaction is a smooth reaction. Alright guys. Another question which I can think of is, why is slate lime used in a high proportion? So much. Is it free of cost? Of course not. Slate lime is used in a high ratio because if by chance the salt gets exposed to the air, do you know ammonium chloride is what? it is a sublimable solid. Of course you knew it. You studied. Ammonium chloride being a sublimable solid, it vaporizes. The dense white fumes come up and they bloody stick to the apparatus. And that's going to be difficult for me to remove it, right? So what I'm trying to do is, I'm trying to be safe. I'm trying to play safe. I want a lot of proportion of calcium hydroxide so that I want to save myself from washing this. Washing in the sense, I don't want the ammonium chloride to vaporize out. I want them inside the solution. All right. The next question. Let's go to the part B. Now this was all about part A, right? I've covered everything. Okay, the nook and corners are covered for this. Part B, which other drying agents can be used and which we are not using, obviously. I guess we can use drying agents like conc H2SO4. We can use fused calcium chloride. We can use P2O5. Yeah, of course we can. These are the three drying agents which are an alternative. But I'm sorry, I'm not going to use them. Reason? Ammonia reacts with them. Shit, man. So can I say if ammonia reacts with them, the problem is, what is my aim? Tell me, what is my aim? What am I trying to do? I'm trying to dance or what? No, I'm trying to collect. I'm trying to collect ammonia gas. So if ammonia is gone, what will I observe? Okay, will I observe? Nothing. Nothing will be in my hands. I'll be empty-handed. Hence, can I say, I want ammonia not to react with these three cartoons. The reaction is, we have ammonia plus conc H2SO4, the first cartoon. It gives me ammonium sulfate, NH4 2SO4. Now, if you happen to balance, I've just by hearted it, alright? We have 2 nitrogen, right? 1 sulfur, 6 and 2, 8 hydrogen, 4 oxygen, that's balanced. Another reaction, ammonia reacts with P2O5. Of course, ammonia reacts with P2O5 in the presence of water, that is, moisture is also there, to form ammonium phosphate. That becomes NH4. Phosphate is PO4 3 minus. That's NH4 3 PO4. If you balance, you need 6 out here. I said I'm not balancing in depth. 10th standard, you all should know how to balance. 9th, I have taught. Yep. And 10th also, initially, in few chapters, I have given importance to balancing. Alright. This is 6 nitrogen. This is 3 nitrogen. So make a 2 out here. 2 phosphorus. 5 and 1, 6 oxygen. Anna, the oxygen is not proper. Wait. Hydrogen. 6 3s are 18 and 2, 20 hydrogens. And that's going to be 12. 2s are 24. I need 4 more. Alright. To get a 4 more, if I put a 4 out here. Listen, no, a 2 out here. I need 4 more. So 18 and 4, 22. Sorry. That's 18 and I need 6. Right? 6 I want. So 3 out here. 6 plus 18, 24. And oxygen is 5 plus 3, 8. 8. Balance. And we have the third cartoon. Ammonia can react also with fused calcium chloride, forming CaCl2 dot NH3. To be very precise, it is 8NH3, 8NH3. So the reactions take place and I lose my ammonia gas. The next answer is, why the hell is this jar inverted, tilted? Because ammonia is lighter than air. Ammonia is lighter than air. And obviously, everything which is light goes up. Air is pushed down. So ammonia pushes the air down. And can I say it is collected by the downward displacement of air? So that is the collection. Ammonia is collected by downward displacement of air because it is lighter than air. Also guys, also remember that ammonia cannot be collected over water. Do you remember HCl, hydrochloric acid, is highly soluble in water. Similarly, ammonia overtakes hydrochloric acid. Ammonia is much more soluble in water as compared to even HCl. Shit. And I can say HCl and ammonia both are highly soluble in water. One volume of water dissolves 702 volumes of ammonia. HCl was only 452. This is 702, overtaken, beaten the record. So I can say one volume of water dissolves 702 vols of ammonia. So it is highly soluble in water. So it cannot be collected over water. So I have actually covered up tremendous amount of question answers. One more thing I can say is, why is ammonium nitrate not preferred? Because a nitrate, NO3 1 minus, ammonium nitrate especially, again is a bit exothermic reaction. So the ammonium salt preferred is ammonium chloride. Alright, so this was my just one answer. Laboratory method of preparation. Yeah, a gentle heating is done. If heating is not done, it's okay, no problem. Because out here in the reaction, I have not written any sort of a delta or something. So gentle heating for a for a smooth reaction. Else, it's okay, no problem at all. Right? Go through this, and then we are gonna step back to our second answer. All right, guys. Let's start with the preparation of ammonia using something different, using metal nitride. However, this method is not preferred. The reason is metal nitrides are quite expensive in nature. And the method which I am telling you right now is not that simple. It has many more things associated with it. However, in our syllabus, it's a very simple process which is given. Preparation of ammonia using metal nitride. Let's see. First, how to prepare a metal nitride. That's important. So remember this. If I talk about this as my second answer, yeah, obviously, because my first answer was about the lab method of preparation, right? The second answer is preparing ammonia using a metal nitride. Alright, so first I can simply write the generalized form. A metal plus nitrogen gas, yep, it gives me a metal nitride. Let's take an example. Magnesium as a metal, calcium as a metal, aluminium as a metal. They all react with nitrogen gas, forming the respective nitrides. Now you should know that magnesium is 2 plus and nitride is 3 minus. So by a crisscross method, you will have Mg3N2, 2 plus 3 minus, same, Ca3N2, and this is Al3 plus, NH3 minus, it becomes Aln. I call this as Aln. Now, talking about the balancing part, 3 magnesium, you're going to have a 3 magnesium, a 3 calcium, alright, 2 out here and a 2 out here. So I form metal nitrides. Remember, a metal nitride reacts with warm water. The metal nitrides undergo hydrolysis. What is the word I used? Hydrolysis. Hydrolysis, hydro means water, lysis means breakdown. Breaking down of a compound with the help of water, damn, that's hydrolysis. So now, metal nitrides, they undergo a hydrolysis reaction. Breaking down of a compound due to water. So these metal nitrides, the 3 of them, yep, they react with warm water. So we have Mg3N2 we have Ca3N2, and all of y'all we have ALN, ALN. They all react with warm water. I'm not writing warm everywhere, please, yeah, come on. To form a metallic hydroxide. This will be magnesium hydroxide. Mg is 2 plus and OH is 1 minus. So MgOH twice. Same calcium hydroxide and aluminium hydroxide. An is 3 plus, so it will be thrice. And giving me ammonia. So if I happen to balance it out, yes, 3 magnesium, there can be a 3 out here. Alright, 2 nitrogen. To make a 2 nitrogen, I should put a 2 out here. Let's try how many oxygens. If there was a 3, there will be 6 oxygen and 12 hydrogen. So 3, 6, I guess, yes, it's done. So what we do is simple. 3 magnesium, balanced magnesium, 2 nitrogen, 2 nitrogen. Nitrogen is also balanced. Let's check out. Oxygen is 3 2s are 6. To make a 6 out here, obviously. 12 hydrogen, 2 3s are 6 plus 6. It's going to be 12 hydrogen. So I get the first equation as balanced. Talking about the second equation, 3 calcium, 3 will be out here. Fine, perfect guys. 2 nitrogen, 2 out here. The balancing portion left out is oxygen and hydrogen. Being very monotonous like the previous one, it's going to be the same, 6. And the last one, we have 1 aluminium, 1 nitrogen, going perfect in the order. 3 oxygen and 6 hydrogen. So if I put a 3, there it is, it's balanced. So guys, can I say that if I happen to just club it up, I can claim that a metal, simple guys, simple, a metal plus nitrogen, it gives a metal nitride. Yep. And a metal nitride plus warm water, it gives me metallic hydroxide plus the one which I am interested in, ammonia gas. There it is for you all. Right? So remember this entire process. This is like a generalized view, an overview of what we have done. However, as I said, this process is called hydrolysis because the breaking down of a metal nitride, the compound metal nitride, to give ammonia with the help of water is called hydrolysis. All right. Now, as I said, the entire apparatus which we are going to use out here also, drying agent to remove the moisture, it is same as the laboratory method of preparation. So I'm not making a diagram with respect to that. However, as I said, the metal nitrides, to make them is not that easy. This I have written a very simple process. They are expensive. So this method is seldom used, not much used. So this was my second answer for you all. Alright. If I talk about the physical properties as my third answer, the physical properties of ammonia gas. Alright, third one. The first pointer in the physical properties. Alright, first, ammonia gas is basic in nature. So students, if it is basic in nature, it turns a red litmus, a moist, to be more precise, a moist red litmus paper, it turns into blue in color. That's the first pointer. Second pointer, talking about ammonia as a gas, the physical nature. It's a base, so can I say it is bitter in taste? Bitter to taste. Third pointer, ammonia gas, it reacts with water to form liquor ammonia. Now, that's called NH4OH. We also call it as ammonium hydroxide, right, with this, and that is basic in nature. It's a weak base, to be more precise, it's a weak alkali. So what did I speak? I spoke ammonia. That doesn't come under physical properties though, right? But just can I say, talking about the odor of ammonia. Ammonia is pungent odor. Again, pungent, I can also say choking, yeah. Hey, come on, yeah. Basically, what is ammonia? Yeah? When you do urine, susu, urine, the smell which comes from the toilets, yeah, that's ammonia type of smell. It's urea. It's urea. It's a content of ammonia. So it's a pungent choking odor. Yeah. It's horrible, right? These three properties, I guess, are sufficient enough, right, to tell me about the physical properties. It is colorless. So we've spoken about the odor, the taste, the color, and the action on the litmus paper because it's basic in nature. So it's colorless. So you can remember about these four physical properties of ammonia. Go through these things and then we're going to start with the industrial method of preparation, which is called the Haber's process of ammonia. The fourth answer, it's going to be the Haber's process, the industrial method of preparation. Haber's method. Now we exactly have three chambers, right? The chambers look as follows. My diagram of chambers always is going to be something like this. Two inputs, then the next chamber, and then the final chamber. Alright, fine. Let's start. And this is the outlet. Okay, the first chamber is called a compression pump. Compression pump. The second chamber is called electrically heated catalytic chamber. And there is also a heat exchanger out here. With heat exchanger. And look at the spelling, nice that. Sometimes for a change, yeah, exchange. Don't do this in exam, right? Exchanger. And this is condenser with cooling pipes. Right. So these are basically the three chambers which are involved in the Haber's process. Okay. The inputs are nitrogen, dry, please, pure, please. So in simple language, pure, dry nitrogen. And the other input from the other end is going to be pure, dry hydrogen. Now, why should they be pure? Because if impurities enter along with them, the impurities will poison the catalyst. When they will poison the catalyst, the efficiency of the catalyst will reduce. So the reaction will not be smooth. Remember. So the first thing, guys, which impurities should be devastated? The impurities like carbon monoxide, carbon dioxide, H2S, etc. may enter and poison the catalyst. So not good, not good. Which catalyst? Just hold on, I'm going to write down the reaction. Just hold on. So they have to be removed. Therefore to be purified. Also, how are you going to purify them? How? In order to purify nitrogen, we have fractional distillation. I'm not entering into the depth. We have done this in 8th, 7th, 9th standard. And in order to purify hydrogen, we have Bosch process. 9th standard hydrogen chapter. Come on. Bosch process. You have heard about it. So by using these different processes, we can get them pure form and remove the moisture. So now they both combine together in a compression pump. Compress. Compress means pressure increases. Downward pressure. Come on, more pressure. So the reaction takes place is as follows. Nitrogen reacts with hydrogen It's a reversible reaction forming ammonia and approximately 22 kilocals approx. Tremendous amount of heat energy. Highly exothermic reaction. The temperature used out here is approximately 450 to 500 degrees Celsius. The pressure used is approximately 200 atmospheric pressure. They have written 200 to 900. But remember, such a high pressure cannot be applied because the machine, right? The what do we say? We call this as a reactor. Will not be able to sustain such a high pressure. Will not be able to withstand such a high pressure. So the pressure used is tentatively somewhere around 200 atmospheric pressure. The catalyst used in this reaction is Fe. We can also use Fe2O3. And the promoter enhances the efficiency of a catalyst. It pushes the catalyst. Work hard, man, you will succeed in life. Promoter used is molybdenum, or you can use K2O and Al2O3. You can also use these as the promoters. Promoters will never work on the reactants. They will only work on a catalyst. Remember that. So these are the conditions and a highly exothermic reaction. Alright. Now what happens is, in the compression pump, both of them, nitrogen and hydrogen, they combine together. Not 100% combination, but yes, majority of nitrogen and majority of oxygen, they at least come close together because of the external pressure. In the next chamber, which is electrically heated catalytic chamber, the heating takes place and the reaction takes place. So guys, can I say nitrogen, hydrogen which have entered, they are going to combine together. In the next chamber, we have ammonia and we have the left out nitrogen and hydrogen. Remember, 100% combination will never be possible. There will always be some proportion of hydrogen and nitrogen left out. What they are stated or what they are called is, we call them as residual. I call them as residual hydrogen and residual nitrogen because they are not combined and they are going to go further into the next chamber. So now, in the next chamber we have three gases. We have ammonia, we have the residual nitrogen and residual hydrogen in the last chamber. You will ask me, sir, what is the heat exchanger used for? Heat exchanger, whenever the combination between them takes place. Combination means whenever a nitrogen and a hydrogen tries to combine together, there is always an exchange of heat between them, as a result of which they come close to each other. That's heat exchanger. That's what heat exchanger does. Alright, and I will just do heating initially for a small period of time, because isn't the heat produced sufficient enough to carry on the entire reaction? Alright, after this, can I say what am I skipping out on it? I spoke about the impurities, the method of purification. We spoke about the entire promoter catalysts which are going to be poisoned and which we need to sustain, refrain them from poisoning, help them to prevent getting poisoned. Temperature used. If you use higher temperature, the decomposition of ammonia takes place. If you use a lower temperature, the combination of nitrogen and hydrogen may not be proper. If you use a very high pressure, the reactor will not be able to withstand that. And if you use very low pressure, very low pressure, again the proper combination of both of these idiots won't take place. So can I say this is called Le Chatelier's principle. This is there in 11th standard in depth, 11th or 12th college section if you take science as a subject. However, right now just don't go into much depth of it, right? Alright. After this, in my third chamber we have landed. Third chamber, students, we have three gases. Nitrogen, residual, which is left out, which is not recombined, residual hydrogen, and we have ammonia. I'm interested in only ammonia. So what I do is, I set up the temperature, the pressure and the temperature of the third chamber as follows. So in the third chamber, that is condenser with cooling pipes. In this chamber, what happens is we have three people. We have residual nitrogen, residual hydrogen, and the ammonia. I am interested in only obtaining ammonia. So what I do is, ammonia, okay, the temperature of the last chamber, okay, the temperature is made up till minus 33 degrees Celsius at 8 atmospheric pressure. At this temperature and pressure, the ammonia liquefies. It becomes liquid ammonia. We obtain liquid ammonia. Remember, liquid ammonia does not have any water content. The name is given because the state has changed from ammonia gas to ammonia liquid in nature. However, there is no presence of water in liquid ammonia at all. Now, nitrogen and hydrogen, to convert them into a liquid form is very difficult. We'll need to go up till minus 196 degrees Celsius to liquefy nitrogen, and we need to reach minus 256 degrees Celsius to liquefy, to obtain liquid hydrogen. So these temperatures, they go way below to low. So first what I attain, okay, while freezing is minus 33 degrees Celsius. So I get the ammonia in liquid form. I get this ammonia in which form? In liquid form, guys. In liquid form. Remember one thing. So this is called liquid ammonia, which can be collected from the bottom. However, the residual nitrogen and the residual hydrogen, which are still in the gaseous state, they need to be reused. So what we do is, we tell them, oh come on, get lost from this chamber, come back when you form a bond between yourselves. That means they are thrown back. They are thrown back, okay. The residual nitrogen and residual hydrogen, they are thrown back into the compression pump, and they are told, they are ordered that you go back, right, combine, and then only enter into the forward part, into the further chambers. Always remember this. So this was a beautiful process. We are not even losing out on the nitrogen and the hydrogen. Remember, in this process, the amount of hydrogen used, okay, the amount of hydrogen used is way too more as compared to nitrogen. Because remember, in ammonia, the ratio of nitrogen is to hydrogen is 1:3. That means when you give an input of the reactants nitrogen and hydrogen, you need to be cautious that if you are giving 10 molecules of nitrogen as an input, you need to minimum give 30 molecules of hydrogen as input. Because in a combination of ammonia as a bond, hydrogen holds a larger value. Hydrogen is required in more proportion, in more quantity. Right, guys? Fine. So this was the end of my fourth answer, which is your Haber's process, which is the industrial method of preparation. Okay, we've spoken about the physical properties, the metal nitrides, the lab method, and the industrial method. Again, the same old thing. Ammonia, right? It is highly soluble in water, 702 approx. So we have spoken about that in the laboratory method. Talking about the fountain experiment now, the fifth answer. We have done this in HCl. It is the same thing, a minor change. Okay, in a fountain experiment, okay, you take a round bottom flask, fill it with ammonia gas. Fill it with ammonia gas. There is again a dropper. filled with water. We have a jet tube which pops up out very thin tube, and the lower end of the jet tube is in a beaker having litmus solution. This is a red litmus solution. Okay. Now what happens is, whenever you press the dropper, couple of droplets of water come out. When the droplets come out, we know ammonia is highly soluble in water. So what happens is the ammonia gas, most of it gets dissolved in water, and ammonia plus water, it gives me ammonium hydroxide, NH4OH, which I call it as a leaker ammonia, ammonia aqueous, right? We also call it as ammonium hydroxide. So remember this. Alright. Now, this red litmus solution, because of the gas was absorbed by the water molecules, was dissolved in the water molecules, a partial vacuum is created. Because of a partial vacuum, there is a low pressure region. And because of the low pressure, this is an atmospheric pressure which comes from here, atmospheric pressure. The atmospheric pressure pushes the water is sucked up. The water is sucked up in the jet tube, which is actually a liquid solution, and it's actually a red water, but can I say it emerges as a blue fountain? It tells me ammonia is basic in nature. So it turns a red litmus into a blue fountain out here. So this is a fountain experiment. It tells me two things. First, ammonia is highly soluble in water, and second, it tells me about the basic nature of ammonia. So this experiment demonstrates two behavioral patterns of ammonia as a gas or a liquid. Right. So this were my 5 answers. Go through them, and we're going to talk about much more for ammonia. Sixth answer. We're going to prove that ammonia is neither combustible nor does it support combustion. Okay, we have two experiments. Okay, so talking about my next answer, the burning of ammonia in air or oxygen. So we have ammonia NH3 plus O2. Alright, nothing on the arrow, just simple burning of ammonia. It gives me nitrogen plus water. Now this is an experiment, students. First let me balance this. 2 nitrogen, 1 nitrogen. So ideally there should be a 2 out here. If we make a 2 3s are 6 hydrogen. We can make a 3 out here. But 3 is an odd number for oxygen. Shit. So if I double the 3 and make a 6, 3, 12 hydrogen, 4, 2. That's how you get it. So what I'll do is, ideally there should have been a 3 out here, but oxygen will become odd. So I made a double of 3, which is 6. So 6 oxygen, 3, 6 oxygen. 12 hydrogen, 4 nitrogen, 4 nitrogen. That's the balancing. If I talk about the experiment, check this, man. Okay, a glass tube or something which we have, an apparatus, in which there are 2 inputs through which I'm going to send 2 gases. Alright, there are cotton plugs out here. Okay, a cotton plugs out here. What you do is, from one of the input, we supply air. So we have air out here, oxygen, and from the other it is ammonia gas. So we have ammonia gas out here. Initially, when the air is passed, let's not pass the air, let's put it this way. Initially ammonia gas is passed, nothing happens. What I do is, from the top, it is open. Let's keep it open for the moment. Okay, from the top, I ignite a flame. Ignite a flame. Okay, so I take it's like a matchstick or a flame. I ignite it. I keep it out here, and I pass ammonia gas. The flame extinguishes. The flame does not burn. Right. So can I say ammonia does not support combustion, and it also itself does not burn. So I can say ammonia doesn't support combustion, nor does it burn on itself. But now, when I pass air and ammonia gas, they react to form a flame, and the color of the flame is green or greenish yellow. So we get a greenish yellow flame. So we get a green or a greenish yellow flame. That's the color of flame. When did this happen? When air or oxygen was passed. Because of the water, the cotton plugs which are put or which are held out here, they become moist. So the cotton plugs become wet at the end of the experiment, which tells me the reaction has taken place, and the moisture is also a product which is obtained during the reaction. Right? So this is one of the reactions. The second reaction which we'll be talking about is same burning of ammonia but in presence of a catalyst. So we call this as a catalytic or a catalytic oxidation of ammonia. Okay. What we have is we have a test tube in which there is a catalyst called platinum, which is placed somewhere at the bottom of the sleeping test tube. Through this, we pass ammonia dry, and again we pass oxygen. Right. This is a starting process for Oswald's process. When we'll be doing the next chapter or next to next chapter perhaps, which is the nitric acid, we're going to study the same thing. It's a method of preparation, one of the steps of preparation of nitric acid. Alright guys. Then we need to pass it through a flask. Okay. A flask. And then eventually we can collect nitrogen dioxide. That's what's formed at the end. Now listen what reaction takes place. Ammonia, dry ammonia of course, plus oxygen in presence of a catalyst which is platinum, 700 to 800 degrees Celsius. Okay. It forms nitric oxide and water, plus a tremendous amount of heat energy. Again, it's a very, very, very exothermic reaction. Alright, if you balance this out, students, okay, how do we go about with the balancing? Nitrogen is balanced, fine. Oxygen 2, fine. Hydrogen 3, it's an odd number. Let's try putting a 2 out here. Now, if I put a 2 out here, we'll have 6 hydrogen. We need to put a 3 out here. A 3 out here. But a 2 out here makes a 2 nitrogen also. So 2 out here. 2, 2 and 3, 5. 5 is, no. 5 is not an appropriate number. Alright, double it. 4 out here, 4 out here. Nitrogen balanced. 12 hydrogen, 6 out here. Let's try doubling the effect. 4, 4, 6 hydrogen to make 12 hydrogen, 6 out here. Oxygen becomes 10, a 5 out here. That's what you call it as balance. Again, in this process, water is obtained. Check, water is obtained. So here will be water droplets. And the gas which goes ahead is nitric oxide. Nitric oxide is a colorless gas, students. And in this gas jar or a flask, you can say, we have oxygen and we have nitric oxide which enters. The nitric oxide which enters, which is a colorless gas, reacts with oxygen, forming reddish brown gas which is nitrogen dioxide. To balance it, a 2 out here, a 2 out here. That's balanced for you all. So it's like a two-step reaction. And finally, we get a reddish brown colored nitrogen dioxide gas, which can be collected. In this reaction, the heating is only done on a temporary initial basis. Because, can I again say that once the platinum gets heated up, it becomes red hot. Okay, and the exothermic reaction continues the entire process ahead. We don't have to continue a high temperature for a longer duration. Alright, so this is the second experiment and the second set of reaction. So the first set of reaction is burning of ammonia in oxygen or air, and the second is catalytic oxidation of ammonia. Fine, nice one. Both are good ones. Now, talking about the basicity of ammonia as my eighth answer. Ammonia is a very weak base, because if you draw a diagram of ammonia, ammonia has one lone pair. So if I draw a cross and a dot structure, it becomes this way, forming NH3 and one lone pair. And because of the lone pair effect, students, I can say ammonia is a very weak base. Super weak, yaar. It's a very weak base. Ah. So, ammonia, if I get a dry litmus paper or a dry ammonia gas to a litmus paper, nothing happens. Litmus paper remains neutral. So I will say it is neutral to a litmus paper. It is neutral to litmus paper. Because of the weak basicity. Even forget about the ammonia gas. Even liquid ammonia. Liquid ammonia is also neutral to litmus paper, because haven't I told you a few minutes back that liquid ammonia has nothing to do with the water. It has nothing to do with the presence of water. There is no water in liquid ammonia at all. So they both are neutral to a dry litmus paper. But if you use aqueous ammonia, that means if you put ammonia in water, it forms ammonium hydroxide. Now, there are many names for this. You can also call it as a liquor ammonia, or we can call it as ammonia aqueous, or you can call it as ammonium hydroxide. And yes, this is a weak alkali. Alkalis are bases which are soluble in water. So I will say yes, ammonium hydroxide is soluble in water. Not soluble, I will say it dissociates partially. Partially means there is no complete breakup, there is no complete decomposition. Dissociation, right? It is a partial dissociation. When put in water, the ammonium hydroxide partially breaks down into ammonium ion NH4 plus and hydroxyl ion OH1 minus. And because of the presence of OH1 minus, because of the presence of this, which is hydroxyl ion, I can say it turns a red moist litmus into blue color, showing its weak basic nature, the basic action. And this reaction eventually tells me that yes, ammonia as a gas, I'm sorry, it's a very weak base. It's neutral to the litmus paper. But ammonia as a solution in water, the aqueous ammonia, that is an alkali, though weak, but yes, it's an alkali. It turns a red litmus to blue in color. Alright. After this, we spoke about many things, guys, many things. Okay, so after this, let's talk about the next concept, that is your concept number 9th. Okay, the few reactions are as follows. Ammonia, you take ammonia gas first. Ammonia gas in acid, let's take dilute acid, dilute HCl. It forms a salt, an ammonium salt, ammonium chloride. It's balanced. You take another reaction of ammonia gas and react it with dilute sulfuric acid, you get ammonium sulfate. Is it balanced, guys? 1, 2 nitrogens. There should be a 2 out here. Hydrogen is 6 and 2, 8. 8. That's balanced for you. So that means, can I say, ammonia gaseous form plus a dilute acid, it gives me a salt. That's it. That's it. But ammonia aqueous, the liquor ammonia, the aqueous ammonia with water, right? That is NH4OH. If it reacts with a dilute acid, of course it forms the same salt, yeah, NH4Cl, but it forms water also. Now if you balance it, it is balanced. You come on. And another last reaction, NH4OH plus let's take dilute HNO3, nitric acid. Again it forms a salt, ammonium nitrate, NH4NO3 plus water. Is it balanced? Yep. So what can you make out from this? What can you make out? I can say gaseous ammonia and aqueous ammonia, they react differently. Aqueous ammonia forms the same salt as gaseous ammonia, but in addition to it, it releases water. So that is the only difference between the two reactions. So go through them. Okay, the 9th header were a few reactions with ammonia gas and ammonia aqueous. Go through them. Talking about the chemical properties of the ammonia gas, the 5 reactions which are very important. Let's start with the next answer, chemical properties. Alright, in the chemical properties, students, the first reaction, let's take with iron sulfate, Fe, that is a 2 plus Fe, FeSO4. Now what we do is understand, in a test tube, I take iron sulfate, yes, and I add ammonia solution, that is NH4OH, liquor ammonia. The reaction takes place forming a precipitate FeOH twice. This is a dirty green colored precipitate and FeOH twice and NH42SO4, a salt, ammonium sulfate. So the color of the PPT is a dirty green PPT. You need to write a PPT, please. Now what I do is I continue the reaction. In the test tube, first we put these two as a reactant, we obtained this as the product. So at the bottom of the test tube, you will have a dirty green precipitate, and just above that, there will be a solution of ammonium sulfate. What you do is, in that same test tube, right, you add more of ammonium hydroxide, add more of that. Nothing will happen. The reaction remains the same. So can I say, on addition of excess of ammonium hydroxide, the dirty green precipitate will be as it is, no change at all. We take the second reaction. Let's take a Fe3 plus salt, that is FeCl3. Okay, iron 3 chloride plus aqueous ammonia NH4OH. It gives me FeOH thrice plus NH4Cl. Okay, I'm not balancing. I think it's already balanced. Fe, 1 nitrogen, 2 nitrogen. So I need to make a 2 out here. Come on. Then hydrogen is 8 and 2, 10. Hydrogen is 8 and 2, 10. Perfect. Oxygen 4 and 2, 6. Oxygen 2 and 4, 6. That's balanced for you. Talking about the next one, we have a precipitate which is a reddish brown precipitate. Alright, if you balance it, chlorine 1, chlorine 3, can you make a 3 out here? 3 nitrogen, alright. Hydrogen 15, hydrogen 12 and 3, 15. That's balanced for you. A reddish brown PPT. Again, in this solution, in this mixture, in a test tube, if you pour excess of NH4OH, nothing will happen. This remains the same. The third reaction. We spoke about Fe2 plus salt. We spoke about Fe3 plus salt. Let's speak about lead. Yes, lead nitrate. Let's take something different. PbNO3 twice. It reacts with aqueous ammonia NH4OH, giving me a chalky white precipitate of lead hydroxide plus ammonium nitrate NH4NO3. Again, to balance the stuff, the color is chalky, a chalk colored white PPT. Alright, now if you talk about nitrogen 2 and 1, 3 nitrogens, you have 2 out here. That's an odd number. Lead is 1, lead is 1. Nope. Later, it's balanced. How much? 2 and 1 as I said. And that's an odd number. I'm getting confused. Chuck the nitrogen. Talking about hydrogen. 5, 2 and 4, 6. It's an odd number. Let's try to make this even. If I make this 2, it becomes 2 and 2, 4 nitrogen. This is 2 out here. Let's make a 2. 4 nitrogen. 5 2s are 10 hydrogen. This is 4, 8 and 2, 10 hydrogen. That's it. Let's talk about oxygen. 2 and 6, 8. 2 and 6, 8. That's balanced for you. Alright. Again, in this same reaction, you add more excess of NH4OH, nothing happens. So, in the 3 reactions of Pb2 plus, Fe2 plus and Fe3 plus salt, on addition of excess of NH4OH to the products, nothing happens. The precipitates are sustained. But the fourth one, talking about zinc and copper, guys. Let's talk about zinc sulfate. Reacts with NH4OH, right? It gives zinc hydroxide as a PPT, a gelatinous white precipitate. A gelatinous white PPT. Plus ammonium sulfate. Yeah, NH42SO4. That's nice, that's nice. If you balance this, zinc balanced, 2 nitrogens, 2 nitrogen, 10 hydrogen, 8 into 10. That's balanced for you. Check it out. Pay attention. I again proceed with the same process. I take a test tube, I take both of these, I react them, I get a gelatinous white PPT of zinc hydroxide and ammonium sulfate. Now, in that test tube, I add excess of ammonia. Reaction takes place. Yes, it does. It's a 2-step reaction. Check this, guys. So, in the test tube, we already have zinc hydroxide. We already have ammonium sulfate. Now, I add excess of ammonia solution, that is NH4OH. I get a complex salt with water. And that complex salt name is tetraamine zinc sulfate. Check this the way I write it, guys. Tetra, that's 4. Amine, NH3. Zinc, Zn. Sulfate, SO4. That's how you write it. Tetraamine zinc sulfate. And this is a clear, colorless solution. Oye, it is not a PPT anymore. The precipitate vanishes. It becomes a clear, colorless solution of tetraamine zinc sulfate plus water. Fine. Right with this? So it's a two-step reaction. It's a double stepper. So for the first time in the history of mankind, in this chapter, we've seen a two-step reaction. The similar thing goes for copper also. Check it, guys. The fifth reaction, the last one. You have copper. Let's take a salt, copper sulfate, yeah, monotonous, it's okay. Manage it. Plus NH4OH. Something new here. I'm just writing the reaction. It gives copper hydroxide. Now that's a PPT, a pale blue precipitate. The color, you need to buy her this color, yeah. Come on. Plus ammonium sulfate again. Now that's balanced. I've already written a 2. Again, in this reaction, you excessive ammonium hydroxide solution, you pour it. So it's again a two-step reaction. So you have, from here I need to start, copper hydroxide plus, it's a PPT for the moment. In the test tube, we have these two things already together with us. You pour excess of ammonia, NH4OH solution. It gives tetraamine copper sulfate plus water. Now this color, it's not a precipitate. Look, there is no downward arrow. Nope. This is called tetraamine copper sulfate. And the color of this is deep blue or inky blue. It is either deep blue or inky blue, but it's not a precipitate, it's a clear solution. So these are few reactions in which two of them, the two salts, the zinc and the copper salt, are a two-step reaction, whereas the other ones, they're just a single-step reaction. Right, guys? Yeah. Now, talking about few more reactions and one beautiful property of ammonia acting as a reducing agent. So first go through this and then we are going to encounter about those three things. Ammonia as a reducing agent, reaction of excess of ammonia with chlorine, and reaction of excess of chlorine with ammonia. Just check this out. Ammonia gas as a reducing agent. Let's begin, guys. What we're doing is we take a sleeping test tube, okay, a hard glass test tube. We pass ammonia gas, NH3. Yes. And there are two substances which are placed at the bottom. One of them is lead oxide, PbO, and another is copper oxide, CuO. The color of lead oxide is buff yellow. It's buff yellow. And the color of copper oxide, it is black. These are the original colors. And what we are doing is we are gently heating them. We're gently heating both of these compounds separately. Ammonia acts as a reducing agent. It takes away the oxygen from lead oxide, forming lead. So what ammonia does is, ammonia reacts with PbO. Okay, it reduces PbO. It's a reducing agent, sorry. So can I say ammonia reduces PbO, takes away the oxygen to form Pb. The color changes. That's how we come to know the reaction has taken place. along with formation of water and nitrogen gas. Now the color of PbO, as I said, it is buff yellow, and the color of lead, Pb, is a grayish metal we can say. And whenever there is a color change, I come to know, damn, the reaction has taken place. Okay, from here we have two gases which emerge out, liberated. They are first passed through a U-shaped condenser tube in which the water is condensed. The water vapor gets condensed into water. So out here, yeah, this is called condensed water. The water gets condensed out here. So eventually, can I say Pb is a residue which is left behind? Water has been condensed, the water vapor has been condensed, and eventually I am left out with nitrogen gas, which is collected over a test tube, an inverted one or an inverted jar having water. So there is water out here. And you can say this is like a water beaker. A beaker, a trough or something having water and an inverted cylindrical jar, and there is obviously, you can't have a outlet out here, it will be somewhere from the bottom. Come on, yeah, it's obvious. But can I say that from here we have two people coming out, two idiots, water and nitrogen, and from here it is only nitrogen. This is H2O. The nitrogen is sparingly soluble in water. Very little quantity of nitrogen is soluble in water. Nitrogen goes up, and once the nitrogen gets accumulated, it pushes the water down. Hey dude, go down. I want a space to be out there. So can I say the water is displaced downwards? So can I say the nitrogen gas is collected by downward displacement of water. Downward displacement of water. That's it. And it is very sparingly soluble in water. Apart from this, I have not written one more reaction I should have. Ammonia also reacts with copper oxide, forming copper residue, H2O, nitrogen liberated. If you happen to balance it out, students, lead is balanced, hydrogen 3, hydrogen 2, nope, multiply by 2, multiply by 3. Alright, so we have 3 oxygen, 3 lead. That's balanced. Look, I'm going fast in balancing because come on, yeah, 10th standard kids you all are. You're doing balancing since 7th, 8th, 9th, 10th. And come on, 10th, in one particular reaction, you can't expect me to balance slowly. It gets monotonous. Yeah, please. Yeah, right out here. 3 hydrogen, 2 hydrogen. So 2 out here, 3 out here. 6 hydrogen, 2 nitrogen. Perfect. 3 oxygen, and 3 copper. That's balanced for you all. And the color change, of course. The copper oxide is black in color, and copper is reddish brown or brownish red, something like that. Sometimes copper is also pinkish brown. Okay, it also depends upon the impurity and the purity of copper. Let's not enter into that. Fine, so these are the color changes. So when I see the color changes out here, I come to know, yes man, the reaction has taken place. Fine, so this was my answer which spoke about the reducing action of ammonia. Yeah, that's my nice answer. It's a very important answer from board exams point of view. All right, the next one is the reactions. Excess of ammonia with chlorine. Let's see this reaction. It is a reaction which is based on partial equation method. Now these 3 words, partial equation method, we have heard about in ninth standard, where most of the schools they eliminate this method. Let's learn about it. It's simple. Look, I take ammonia, ammonia, come on, and I react with chlorine. It forms HCl and nitrogen gas. If you balance this out, if I put a 2 out here, I'll be in a problem because hydrogen is 3. So make hydrogen even. Hydrogen becomes 6. 6 out here. Chlorine 3. Nitrogen 2. That's balanced. This is the first step. So in a test tube, I take ammonia, I take chlorine, I stir it, I get HCl and nitrogen gas is liberated. Fine. So I collect the nitrogen gas. Yes. What is left in the test tube? Hey, come on, tell me what's left in the test tube. HCl is left in the test tube. I add more of ammonia to that HCl. So now I can say excess ammonia NH3, guys, added to the test tube. Now the test tube already contains 6 HCl. So obviously the 6 HCl was present initially in the test tube. In that same compound, I'm adding ammonia. So obviously I have to add the 6 out here. It reacts to form dense white fumes of ammonium chloride. And if you balance it, it's 6,6. So you will say, sir, what's this crap, man? Already the reaction was balanced. Then why did you put a 6 out here? Come on, I put a 6 because there were already 6 volumes of HCl present in the test tube, right? Fine. And you add this up, man. So you get 8. Always remember, on the same side of an arrow, things have to be added up. And on the different sides of arrows, things can be cut, cancelled, brutally eliminated. So you eliminate catch again. Yeah, I loved it. So HCl, 6 HCl is eliminated completely. You add it. So you have excess. That word should be written, please. 8 ammonia plus 3 chlorine atoms or molecules, sorry. It gives 6 NH4Cl plus nitrogen. This is my final reaction for y'all. Yeah? After this, the next reaction. Excess of chlorine plus ammonia. That's a simple one-step reaction. That's not difficult at all. So you have ammonia plus excess, please write down here, mentioning, it forms HCl plus NCl3. Now, all of y'all, this compound which I've written out here, we call it as nitrogen trichloride. What do we call it as? Nitrogen trichloride. And it is a yellow colored explosive liquid. It's a liquid, yellow explosive liquid. Danger. Balance it up, guys. So 3 and 1, 4 chlorine, can make a 2 out here. 3 hydrogen, 1 hydrogen. Shit, you make a 3 out here. Hydrogen is balanced, nitrogen is balanced. How many chlorine? 3 plus 3, 6. 3 out here. 6 chlorine. So that's a balanced version for y'all. Alright, so we studied about beautiful things today. Right now we studied about the reducing action, the excess ammonia, the excess chlorine, the color. One more reaction, a very important one. Formation of nitrogen using ammonium salt. I'm writing the heading. A bit more, skeptical about what I spoke. Most of them are. Formation of nitrogen, using ammonium nitrate. This usually comes now, ammonium nitrite, not nitrate, nitrite. This usually comes in the prelim papers of different schools which we make our kids solve, right? So it's a nice reaction. First, how on earth will you prepare ammonium nitrite? Nitrite. Let's check this. It's a two-step reaction. You take ammonium chloride, an ammonium salt, a simple one. React it with sodium nitrite, NaNO2. Ammonium chloride, sodium nitrite. It forms ammonium nitrite, NH4NO2 plus sodium chloride. There I got ammonium nitrite. Ammonium nitrite reacts, it doesn't react. You need to heat it. You burn it. You heat it. It gives you ammonium nitrite on heating should give you, what do you have to prepare? Nitrogen, yeah, and water. So it gives you water plus nitrogen. That's the reaction. If this, the above equation is a balanced equation. Let's think, look at this one. 4 hydrogen, 2 oxygen, 2 nitrogen, balanced. So this is the way in which I'm going to decompose ammonium nitrite to get nitrogen gas. Right. So just go through these reactions and then we will attack almost the last part, the last portions of the chapter. Yep. The last portion of our chapter, the chemical properties. Now the best part is that the chemical properties are already completed except for one. We have studied about, we have studied about NH4Cl, yes. NH4Cl, that is dense white fumes of ammonium chloride are formed. Now when will they be formed? When will they be formed? When you react ammonia with dilute HCl. So isn't this one of the properties? For example, you take a glass rod, dip the glass rod in ammonia solution. Ammonia solution is going to be NH4OH, that is liquor ammonia. So dip the glass rod in ammonia solution and pass HCl through it. You will find a dense white fumes of ammonium chloride are formed. So this is one of the experimental, calculations which we do. The first one. The second one which we can speak about is the copper sulfate. I hope you remember in the copper sulfate experiment, we used to take copper sulfate plus ammonium hydroxide. It gave me copper hydroxide, which was a pale blue PPT. Plus, it gave me a salt. When I add excess of ammonium hydroxide, when it is added in excess, what is formed? A deep blue or an inky blue solution, a clear solution of tetraamine copper sulfate. Yeah, that was a deep or inky blue. Now this is again an observation. These are all repeated reactions for ammonia. Okay. The third chemical test which we can speak about is Nessler's reagent. This is a new one. Nessler's reagent. Now Nessler's reagent is said to be potassium mercuric iodide. Potassium mercuric iodide. It is said to be this way. When I pass ammonia through this solution, first it means the solution turns pale brown. And when we add excess of ammonia in this, the pale brown solution turns into a brown precipitate. So in excess of ammonia. So always remember, a Nessler's reagent on reaction with ammonia, it turns pale brown, and on addition of excess of ammonia turns into a brown PPT. So these were about the chemical tests. And the last portion of the chapter to wind up with are few uses. Remember, the liquor ammonia, that is ammonia with water, and that's nothing but NH4OH. Ammonia with water is said to be liquor ammonia, right? Liquor ammonia, what is the use of liquor ammonia? Remember, it is used as a cleansing agent. Cleansing agent. Yep. Now, what and why is it used as a cleansing agent? Because liquor ammonia, it emulsifies, dissolves, dissolves fats and grease and oil stains. So all these stains can be removed using liquor ammonia. Hence, it is used as a cleansing agent for cleaning panes, the windows, the panes of the window, the porcelain articles, for removing the stains from the clothes. Yeah, liquor ammonia is used for those purposes. However, in contrast to this, we have liquid ammonia. Liquid ammonia is ammonia only in liquid format. There is no trace of water. Liquid ammonia, it is used as a refrigerant. It is used in refrigerators for cooling purposes. How? Why? Because liquid ammonia has a high latent heat of evaporation. I didn't understand. Now, what do you mean by high latent heat of evaporation? It takes a lot of heat from the surroundings. It makes the surroundings cool, and it turns from a liquid format to a gaseous format. That means a liquid ammonia, right? It is liquid. The state is a liquid state. Whenever it absorbs the heat from the surroundings, come on, it's taking heat inside its body. So can I say the surroundings become cool, and it takes a lot of heat, and then only it changes the state from a liquid state to a gaseous state. So it has a high latent heat of evaporation. Thus, it's used as a refrigerant. One more quality, it is highly volatile. Okay, and it brings down the temperature of the surrounding to a great level. Okay, so it cools the surrounding to a very good level. So I can say liquid ammonia is used in refrigerants. Liquor ammonia is used as an emulsification purpose, that is used as a cleansing agent. Alright guys, so this ends my chapter of ammonia, right? Hope you've understood this chapter, and if I've gone erroneous at any of the portions, please put it to my notice, because in a flow, in the natural process of explanation, there may be a point or two where I may have spoken something else and I may have written something else. Might be a possibility. I've tried to reduce the errors, tried to make it errorless, but still we are humans. We are here to learn, guys.